Hello students. So in this machine learning project basically or tutorial, we are going to discuss about how to build a let's say species similarity application, or some cluster kind of thing. Let's say human identifier, okay, or whether let's say identifying or classify a set of images compared to a set of another images. So let's say we have two images, cat and dogs. Okay, so we are going to build one Siamese network that will classify, okay, how much similar is my one image from the another. Okay, so you can think in that way. So you can also train a Siamese network for your different species classification, and you can use a little bit more concept here to implement auto classification methods and all. So yeah, anyways, we are just going to build a simple Siamese network based on fashion MNIST data, and then we'll see the same example with more robust let's say cats and dogs image data set. And what we are going to do, we are going to build one application that will I mean turn to be green, or probably it will output one if our output both the images are cat, or both it will turn to be a zero, or it will turn to be a red if both the images are not cat. So let's say one cat's image and what's one human's image. So it will identify or it will learn to identify the similarities and dissimilarities between the shape of cat and shape of dog. Okay, so that's a pretty interesting thing, right? So to build this kind of application, we use multi-input neural network models, and probably Siamese network is one of the most popular example. So the whole application we are going to build is based on Siamese network. So let's start. Okay, so we are going to use functional API. We are not going to use sequential API for building this kind of modules or this kind of projects, right? As functional API gives us more flexibility to build and join the branches basically of a neural network with other branches or nodes. Okay, so these are all the related stuff are required for this project. You will be requiring TensorFlow as a backend. Then we are going to require model. Then we are going to require input, flatten, dense, dropout, and lambda. And one more thing, as it's only a training purpose project, right? So I'm not going to use neural network, especially convolutional neural network. So just to save some time in training, right? So we are going to use one dense layer as a base layer. And if you wanted to implement convolutional neural network, you can simply implement by copying the network from any other project, right? So yeah, let's get started. So first, if you know, right, what fashion MNIST is, fashion MNIST contains a data set that has 10 levels. Okay, it's 28 cross 28 images, probably RGB images, right? And what's the goal I have just mentioned here is to finding similarities between two products, right? That is the goal. Okay, so where this kind of network will make sense, this kind of network will make sense, let's say in shopping applications, right? Where you have uploaded, let's say, an image of shirt, and the application, based on whatever image you have uploaded, it is showing you same kind of product, right? So let's say you wanted a similar kind of shirt, and you have uploaded images of that shirt. So the product the algorithm runs, the model runs, and then it is just kind of finding all the relative shirts that gives you higher probability or higher similarity score. Okay, so yeah, to build this kind of network, the first thing is you have to create the data set, right? And what will be your data set? Your data set will be pair of images and the labels, right? So what will be the in the pair of images? In pair of images, you will have both the classes, right? The similar class as well as the dissimilar class. Okay, that means let's say in one side we have example, let's say we have a shirt, then in one pair we'll have both the shirts, okay, two shirts, image of two shirts, and that level probably will be classifying as 1 or 0 maybe, oh, sorry, probably let's say for positive we are taking 1, for negative we are taking 0. Okay, so for this case where both the images are shared, that means it's a similarity will be higher, right? It's a similar kind of product, so its similarity score will be 1. And in case of let's say a shirt along with a basketball, right, in that case our similarity score will be 0. There is no similarity, right? So its similarity score will be what level will be 0. Okay, and based on that we are going to build the network, right? So first thing we have to create the pair of images, right? So if you know in fashion MNIST you get the list of images, right? So how we are going to create? So I have written the codes here. Okay, so there is one function. Let me just explain this function first to you. This is a create pair that accepts the indices of the images as well as the images. Okay, so what it will give, it will give you the positive and negative pair and alternates between positive and negative pairs. Okay, so how we are going to create? So this function, it accepts an array of images, right? That means data point, that means whatever this fashion MNIST training data set we are using, right? This data contains. Okay, and as well as this digit indice argument. Okay, sorry, this digit indice argument that we have here, it what it contains, it contains a list of indices where each element contains the indices of images belongs to a specific digit class from 0 to 9, as we have already mentioned. So your fashion MNIST is nothing but classification project, right? Mostly, and in classification you have 10 classes, indexing from 0 to 9. So this digit indices will contain, let's say I have a product named as shirt, and the index of let's say the index of shirt in the leveling as 1 to let's say 2, does not matter. So this digit index contains all the indexes where we have the shirt in the fashion MNIST dataset. So let's say we have shirt in the second example or 10th example or 20th example, so it will contain 2, 10, 20 like that. Okay, so all the digit index it will contains. Okay, so how we are creating this basically pairs. Okay, I mean if you think visually the workflow will be very similar, simple, right? So what we have to contain, we have to we have got the indexes of similar images. So from those similar images we can create one sample of similar pairs, and from those indexes as well, I mean similar to those indexes, we can also create the negative examples, right? That means dissimilar examples. So the first line, what we are holding, or we are creating one variable called n. Okay, so what it is doing, okay, it is finding the smallest number of samples available across all the digit classes, and it is storing it in n. Okay, so what it is doing, the smallest number of samples available across all the digit classes. Okay, that is what it is storing in n. Okay, now next thing, for each digit class, let's say D is the digit class, right? So we have digit class from 0 to 9, as we have mentioned, we have 10 levels, right? How it is creating a positive pairs, right? So let's say this is the digit indices and D is the digit class. So how I am going to get, I am just picking let's say I is one of the variable, and I am just picking the second example, right? So there are for the same index, right? Let's say 2, 10, 20 that we have discussed. So 2 is also one shirt image, and 10 is also, 10th example is also a shirt image, right? So if I take 2 and 10, and I combine these two, it will create one positive pair, right, or similar pair. So that is what this code is doing, right? So let's say this z1 and z2, two variable, it is containing, this is my first shirt and this is my second shirt. Okay, so once this is done, we are just adding, I mean we are getting this indices, right? So once we are getting that, we are just calling that image number, and we are just storing it into the pair as a list of list. Okay, so multi-dimensional array, right? In Python it's a list of list. And in the second case, for dissimilar images, right, how we are finding these dissimilar images? Again, pretty simple. Okay, you create a random class dn, okay, and then you just take one from d and one from dn. Okay, I hope you have understood this point, right? So what it is doing, we already have one class, digit class d, right here. So you create another class dn, which will be different from d, and you just pick one image from d and one image from dn, right? Okay, so this is how you are forming the positive and negative pairs of images. Now next important thing will be, you just does not have to create this pairs, right? You also have to level these pairs. So in the next function, create pairs on set, where we are passing the images and levels. Okay, again sorry. So we are creating the exact same thing, right? So we are creating the images. Images set is already created in the first function call, right? In the second function call, we are creating the images as image sets, and we are combining it with the labels. Okay. So yeah, if you now see the code, I think it will make more sense to you. So the first code, this create pairs, what it will return you. It will return you all the pairs, right, and the labels, right? And the second one will create the pairs and labels combining, right? So this z1 and z2 is nothing but your similar pairs, right? So once you have this z1 and z2, you can easily fetch those images from the data set, I mean from the data set of fashion images, right? And you can add this as pairs, right? So this one will be your one pair. And in the second case, again, you are again picking one random integer, and then you are just adding this random integer with d, and you are doing one modulo with 10. Why we are doing a modulo with 10? Because we have 10 levels, right? So it will give you, every time you perform, it will give you a different number, right? And again from this z1 and z2, by passing this dn instead of dn, we are getting the dissimilar indices, and from this pair we are again creating dissimilar pairs, right? So till now I think everything is okay and everything is clear. And for similar pairs we are adding the level as 1, and for dissimilar pairs we are adding the level of 0. So how it is, I mean how the pairs are creating, now I hope you have gotten the chance, right? So for n will be the minimum sample, right, as we have previously discussed. So this will be the number of pairs that this function will create, okay, and this will be the return value. So it is returning array of all the pairs and their corresponding levels, okay, one at a time. So at in every I mean example, basically you have one similar image insertion and dissimilar image insertion, right? So in that logic you are creating one balanced data set. Now next we are just leveling these pairs with their levels. So how we are doing? So we are just using this np-where clause to filter out the levels, okay, and we are calling this create pairs to get this levels and pairs, okay, and then we are returning the pairs and the levels, okay. So these two function basically by combination of these two, we are getting the levels and the pairs. So this is what required by the network, right? So you require two input, so these pairs will contain both the inputs, and you require the output level, whether it's a similar or dissimilar, right? And it's a simple show image function, just a boilerplate code for showing the images, okay, so that you don't have to write it every time, right? Now to load fashion image data, we are we have done this example, I think, many times. So you always you will get these tuples, right? Train image and their corresponding levels, and test image and their corresponding levels, and you just call this load data method to load the data. So once the data is there, right, you are just reshaping the data as float 32, and then you are normalizing the value, okay, for fast computation. And once it is done, you are creating the corresponding training pair and training levels by calling create pairs on set and passing the train images and train levels. Okay, till now I don't think anyone has any problem. Okay, and similarly you are creating testing pairs and testing levels. Okay, so if you have any problem, right, let's just quickly run this one. I think I already had run this, so you can verify, right? Train image, let's say I'm just to print the first image. Okay, so you can see the shape, right? So this is the batch size, and this is the 828 cross 28 matrix, which is nothing but your array basically, right? So one train image is there, and let's just verify train levels. Okay. So in train levels, you can see all the levels from 0 to 9 in a list format or array format. It's 1D array, right? So that's what we are passing. So we have discussed, right, this values are nothing but your D, right? Okay, and again what we have created TR pairs and TR Y, right? So let's say just going to visualize one pair. So you can see it contains two arrays, that means two images. Okay, and let's say so printing the corresponding levels. Okay, so it's an array of one, that means it's a similar example. I mean, both this array contains similar kind of object, right? That's what we have imputed, right? So if it's a similar product, here we label it as 1. If it is not similar product, we will label it as 0. Okay, so yeah, it will all make sense when you plot, because normally machines do understand this kind of numericals, right? And humans understand better in visualization, and that's why we have created this function, right? This show image, so it will give you a better understanding. So let's say we are creating one pair, let's say on this pair only, right? The pair 1. So let's change this one, and we are calling this show image function, and we are passing this pair, right? And this is the left image, that means the first image, and this is the second image. Okay, and also we are printing the level for it. Okay, so you can see the first one is one shirt, and the second one is a shoe. So both the images are not similar, dissimilar. So what will be the output? The output will be 0, right? For similar we are getting 1, for dissimilar we are getting 0, right? So that is how this input and labels we have created, right? What created. So let's say another index, let's say second index, you take another example, right? So here you can see it, I think it is also a shirt kind of thing, and it is also a shirt, and yeah, the output is 1, right? That means it's a similar product. Okay, if you see 0, I think it will be also a similar product. Okay, yeah, shirt, and you can see it's a similar product. Okay, because how we have created the images, one similar, one dissimilar, one similar, one dissimilar, right? So in 0, 1, 2, 3, so 2 to 3, you will get dissimilar sets. Yeah, you can see one similar, one dissimilar, and that's the dissimilar D0, right? That's how we have created this data set, right? Now once this is understood, now we can print, you know, some images, similar thing that we have just shown. So I'm just skipping this cell. Now let's come to the interesting part, the Siamese network building, right? So to build a Siamese network, what just you know, think or visualize the network. What it will do, it will have two inputs, like so in case of Python or any object oriented programming, you can think it as of a multi-hierarchical visualization of pattern, right? So what this network will contain, it will contain two input and it will provide only one output, right? So it will funnel down. So you have two input, then you have one base network, and both the input will get processed in the same base network and will generate a single output. Okay, so that will be the network. Okay, so yeah, the input will be input from Keras layer. So as you can see, from layers we have imported input, flatten, dense, dropout, lambda, everything, right? So we need not necessarily every time call df.keras.layers that we used to call in the sequentials, right? So what we are doing here, we are first creating one input, and we know it's fashion image data. So keep aside, I don't know what the shape of the batch. My size of image will be 28 cross 28, and we are naming it as base input. Okay, then once you have the data, first thing you have to do is flattening, right? As we have mentioned, we are not applying CNN, right? CNN logics here. Just we wanted to keep our focus heavily on this Siamese network. So in the next project, we have shown how to implement CNN with the same logic, right? So first call this flatten on top of this data or input data. What it will do, it will just flatten this 28 cross 28 to 786, I guess. And once that is done, we are calling one dense layer with a ReLU activation. This is our first hidden layer. Okay, and we are providing 128 nodes. Then we, for doing regularization, we are calling one dropout layer. Okay, and we are passing this dense layer, and once this is done, again we are creating one dense layer. This is our second hidden layer with 128 nodes. Then again with 10% dropout rate, we are creating another dropout layer for doing regularization. And in final, what we are doing, we are creating again 128 layers, third hidden unit, right? So just remember, there is no output like softmax or sigmoid, right? It is a clear dense output layer with 128, which is like another hidden layer in normal regression case or classification case, right? So this is the interesting part, and this is why we use this kind of syntaxing logic or sequential API logic to build this such a diverse models, right? And once we are having this as our output, we are just returning the model with the input, this one, and the output, the final output. Okay, so this is what this base network is doing, where both the image is getting trained, right? Now with this, when you are putting one image in this network, right, it will throw some output. Then again you are putting another image, it will throw some output, right? Then to calculate the loss, right, there is no such kind of loss available in the framework TensorFlow or PyTorch. So you have to write another loss function. Okay, so that will be your custom loss function that you have to write. So once you will write that loss function, okay, based on that loss function you will get the final value, basically. So there is another important thing that you have to understand with this Siamese network and multi-input thing, right? So with this problem, we are also writing not only different network kind of thing, right? we are writing a different loss function altogether. So we are writing Euclidean distance as our loss. So this code I have written down below what it is doing. We will see that. So first let's just run this and let's initialize our model, right? Initial base model, and plot this model. Okay, so you can visualize the model with this plot model function, right? So now visualize that you have your fashion MNIST data set that it is getting, okay, the image data that it is getting, so your input, then base input layer, right? Then you are getting your flatten layer, then your dense, then dropout, then dense, then dropout, then third dense. Okay, okay, and this is where your base network ends, right? So this is your base network. Now two methods we have seen here, right? First one is Euclidean distance, and second one is the output shape of this Euclidean distance, because now we are not first of all returning a single value, a scalar value as a loss. In this case, okay, we are returning the loss with the batch size, right? And then from there we will calculate, we'll create the final loss. Okay, so this Euclidean distance with vectors, what it is doing, it is just computing the Euclidean distance between two vectors, right? Because there will be one output, there will be another output, right? There will be two vectors from two images. Okay, so how we are calculating it? Okay, this vector is nothing but a tuple. Let's say x and y are the let's just hide this for a moment. So let's say this x and y are these two vectors. Okay, and the distance between these two, how we are calculating k dot square of difference between x and y. Okay, this x and y is nothing but your vectors, so this k dot square will do element wise squaring of these vectors by keeping in all the dimension, by keeping only the first dimension, which is generally your batch dimension intact. Okay, and once that is done, then you are doing a summation. Okay, so that will give you the square, that means x1 square plus x2 square and blah 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 stuff, whatever was there, right? And once that is done, then you are just picking up a maximum value, k dot max, this sum square, and this k dot epsilon. What it initiates, let's say your sum of square is returning a negative value or a very small value, right? Very small value. Then what it will do, it can create uncertainty or irregularity mathematical in mathematical computation. To avoid that, we are using one small number. So if my sum of square is less than this small number, then I'll just pick this small number and then I'll do the square root. Okay, so these are some little bit of mathematical terms. If you don't understand, does not worry. When we'll be covering, I think, Hubbard laws and all the custom laws and layers tutorial will deal with all of this. Okay, so this is what your Euclidean distance is. Okay, so if you think for two scalar values, what's Euclidean distance is nothing but x equals to root under x1 square plus x2 square. Same thing in multi-dimension. Okay, and this is how you get the shape of the output. So your output shape will contain the batch shape and 1 as your this loss, right? So that's it in within these two functions. I hope you have understood this base. We have also plotted, right? Then we have understood this custom loss function and the shape. Now let's move on. Now let's create the Siamese model or Siamese network, right? So your input one, the first input, right, that we have seen in the images, right? So if you go into the images, let's say this one is a pair, right? So this one will be your input one and this one will be your input two, right? So your input A, let's say, is a similar kind of input that will fed in the left side of the model, and let's just create the vector output from the base network. So we are calling the base network and we are passing this input on the left side, so it will give us a output on the left side. Similar we are doing with the second image. Okay, as what we are doing, remember, we are just trying to calculate similarity, right? Similarity or dissimilarity between two tensors right now. Okay, so these images are nothing but your tensors. So now again we are passing the second input and we are getting the vector output for these two. And now we have to measure the similarity between these two vectors using the Euclidean distance, right? So we are calling the lambda function from layers, and within the lambda we are passing this Euclidean distance and we are naming it as output layer, and the shape of the output will be the loss function's distance of this Euclidean distance output shape, right? And in this, what we are passing both the outputs of this individual base networks, right? So vector output A and vector output B. So this will be our combined final output. And once we are getting this output, we are creating this Siamese network by specifying the inputs, input A and input B, as a list, okay, or array, and the output model, right? So that's what your output requires. So we are creating two models here, if you see, the base model and the final model, right? So how the final model will look like now? You have the left image, you have the right image, both are coming into your functional basically output. Then it is providing one output, right? Both are going through the same base network and it is providing the output, right? So this is what your Siamese network will looks like. Okay, now what we are doing for Euclidean distance we have measured, right, in this output, in the output. Now in the final output, what we have to do, we have to create one loss again, right? So what loss we are going to create? In case of similarity measure between two vectors, we are going to create constructive loss with margin. Okay, as there is no particular what can I say, there is no two particular fixed range, right? Okay, let's say 0 is similar or 1 is dissimilar kind of thing in a vector space, right? So what we will do, we will penalize if we have a large margin, right? So if the prediction and the actual value does not agree, then if it is a very high value, we'll just penalize that. So that's what it's called, constructive loss with margin. Okay, so as you can see here, this function you provided defines a constructive loss with a customizable margin, which is commonly used in Siamese network for learning the differences between similar and dissimilar pairs. So this type of loss function helps train the model to bring similar pairs close and push dissimilar pairs further apart in the embedding space. Okay, so this is, so you will get one single value that will be for similar pairs very close, let's say close to 0. Okay, as I mean, imagine in a embedding dimension, right, or vector space, right, where you have two vectors, both the vectors are very similar to each other. Then if you do a dot product, what it will you will get a 0, right? You will get nearly a 0 value. And if you have very dissimilar vectors, right, vectors which are reciprocating from one to another, then what you will get, a higher value of when you measure the similarity, right? So that's what we have taken. So this margin is nothing but a scalar value that defines the maximum allowable distance between dissimilar pairs. So if the predicted distance between this between this dissimilar pairs is greater than the margin, the loss will be capped at this margin, which prevents overly penalizing distant dissimilar pairs. Okay, so what it will return, it will return a nested function constructive loss that computes the constructive loss based on the given margin. Okay, and what's your nested function is nothing but this constructive loss, right? So if you see here what we are going to build, so we are going to build a function under function, right? So constructive loss with margin, and that will return you the constructive loss basically ultimately. But first you have to calculate the constructive loss, right? So how we are going to calculate? Nothing but you are doing the square of the prediction element y square, right? And once you have that, you are just doing a subtraction from the margin, and you are taking 0, and this return, right, this return is similar to your you can say cross binary cross entropy kind of loss function, right? That means your binary classification kind of loss. So it is more or less similar to that with a margin, right? So that's what it is doing. So I have written everything here. So yeah, let me just go one by one. That will give you much more clarity. So the what this constructive loss is computing, as described, there is an I guess paper, right? So if you let's just open this, control C. So you can go through the paper to understand what's the constructive loss and what the shapes of the function is, okay, and how to calculate, okay, and how it works actually to figure out similarity and dissimilarity between two vectors, right? And you can see here, okay, in the vector space how it actually looks like. So you can see all the similar pairs have very less, I mean they are very close in the vector space, and all the dissimilar pairs have higher distance, right? So how you calculate, you penalize it with a margin, okay, for higher margin vectors. So yeah, this is the same thing that is implemented in this paper. So first, what we are doing, we are just squaring the predicted distance. This computes the squared Euclidean distance based on pairs, right? So you remember what is our y prediction? Y prediction is nothing but the Euclidean distance prediction, right? In that case, that we have just calculated there, right? So we have calculated Euclidean distance between I mean the difference of these two, right? So whatever the output vector space we got from left image and right image, we created a Euclidean distance between these two, right? So yeah, we are just first squaring up that, and once the square is available, then we know the ground truth. Either it can be 1, which indicates the similarity, either it can be 0, which indicates the dissimilarity, okay? And then y prediction is nothing but the Euclidean distance. I mean, so if it's I mean what distance between the pair of vectors, right? So now how it will work? Margin square. So how we are getting this margin square? We are taking the maximum between 0 and the subtraction between margin and y prediction, okay, and then the maximum value, whatever, either 0 or so. In case of negative value, we are taking 0. In case of positive value, we are taking the positive value, and we are doing element wise squaring up, right? So for dissimilar pair, so we have a ground truth of 0, right? The goal is to ensure the distance between the pair is greater than the specified margin, okay? So what will be my y prediction? It has to be as my ground truth is 0, right? So for dissimilar pair, so the goal is to ensure the distance between the pair is greater than the specified margin, right? So it has to return a negative value here in this subtraction, right? So my y prediction has to be greater than margin, okay, so that it returns a negative value, and here it returns 0, right? That means a dissimilarity can be predicted, okay? And for similar pair, the goal is vice versa, opposite thing, right? As we have 1 in our ground truth, that means it should return a positive value, so that this function as a whole returns a positive value or non-negative value, right? So that's it. And then once these are done, then we can calculate the loss function, which is the mean of all the predictions, okay? So the loss is combined in two parts. In first part, we are multiplying the truth value with the square of prediction, okay? And in second case, we are multiplying the margin square, whatever we have calculated here, this margin square, right? The margin square with 1 minus y truth. So this is for similar pairs, and this is for dissimilar pairs. So what will happen in case of similar pairs? The square distance is minimized, so it will get a minimum value, and for dissimilar pair, the distance is enforced to be at least margin by penalizing the distance smaller than the margin. Okay, so in that way, the overall loss function, we will hope that it will it will remain under the required values. Okay, the overall loss, how we are calculating, we're just doing a average or mean, right, with the overall the entire batches. Okay, so this is how you create one mean constructive loss for a batch of training example, right? So I hope you have understood. It might look like only 2 to 3 lines, but it has a lot of mathematics behind. Okay, so yeah, that's I think if you have very less understanding, you can go to this paper, or you can watch the tutorials where we have greatly discussed how to create custom loss function or custom layers in TensorFlow, right? Then you will have a better understanding of these tensors and all. So once it is done, our loss function we have created, normally in case of loss we used to call, right, the TensorFlow backend functions, but now we have created the loss function, and then only one thing is required, the optimizer. So let's say I'm using a RMS prop with a default learning rate, and once it is done, we can compile. So we are passing the loss with a margin of 1. So for similar pairs, right, the idea should be definitely close to 0. For dissimilar pairs, the target should be more than 1, right? And the optimizer we are passing, and then in fit model, what we have to call? We have to call both the training pairs, right? You remember, right? Left hand side, right hand side. Okay, so both the training pairs and the training levels. Let's say we are training for 20 epochs with a batch size of 128, and we are passing the validation data and validation, training and testing data as well. So I have already run the test to save some time here. Okay, once it is done, how we are computing the accuracy? So let's say in case of my y prediction, if it combines compute the fixed threshold, let's say we are providing 0.5, because at the very last, right, it will give you only one scalar value. So let's say my margin is 1, right? So but we're saying, let's say I know 0 will be my similarity and 1 will be my dissimilarity margin. So if it is crossing 0.5, I am calling it as let's say if it is less than 0.5, I am calling it as a similar, and if it is greater than 5, I am just calling it as a dissimilar pair. Okay, so yeah, again we are calculating the loss from evaluate function. So once you have this, we are then doing prediction on our training testing data. Okay, then we are calculating our train accuracy and test accuracy using this model compute accuracy function that we have just written here, right? This is a boilerplate codes. So yeah, then you can plot the as it is loss function compared to epoch. So we have 20 epochs, right? So you can see there is some fluctuation. Okay, sorry, I forgot to do the leveling here, but this green line indicates the validation, and this blue line indicates the training losses. I hope so. Let me just quickly see the visualization code. Okay, yeah, blue line is for yeah, so this green line is for validation. So you can see a little bit fluctuation, right? So if you are a machine learning engineer, right, by seeing these graphs, you can easily understand which one is training and which one is for testing, right? So once that is done, what you can do, you can create a function. It's what the job of this function, it will plot your true images, pairs, and then it will give you the true value versus the predicted value. Okay, so the true value will be whether there is a similar pair. In case of similar pair, 0. In case of similar pair, 1. In case of dissimilar pair, it will be 0. Like, that's how we have labeled it. And corresponding loss function, right, constructive loss that we have mentioned, will be printed. That will give you the idea. Okay, so we have 0.5 as threshold, right? So anything less than 0.5, will be classified as similar objects. Anything greater than 0.5 will be classified as dissimilar object, right? So here in this first case, you can see it is showing that, okay, it's a similar object. Here in this case, you can see it is showing a dissimilar object. Here also it is a similar object, and you can see the value, it's a very closely related, right? Based on the pixels also you can identify. And here also it is showing that it's a similar kind of object. I don't know whether it's similar or not. Here again dissimilarity, here again dissimilarity, dissimilarity, then here again similarity, dissimilarity, dissimilarity, right? So this is your overall project of how to measure or how to build one similarity application where you can predict let's say cat's image to cat image and dog's image to dog's image, or dog's image to cat image, and vice versa. And you can tell, the AI can tell, okay, this pair is similar. That means both the species in the images looks like a similar species, or this species are not similar, right? So this kind of application, it is very useful. Also in case of retail industry, it is very useful to bring out all the, let's say this is the image, or this is the shirts image that the user provides, and it brings all the related images, right? All the related shirt that matches with this vector. Okay, so this is the tutorial and a basic example of Siamese network. So I also have built one small project based on real data. So this one is with fashion emis, right? So similar network with convolution and real data, right? So you can see I couldn't train it much, right? So only 5 epochs I have trained it. So what you can do, you can take this code and you can retrain, and you can come up with a very good accuracy, right? So here you can see we have first image and second image. First image as cat and second image as dog. The true value is 0. That means there is no similarity, but the prediction is still 0.5, right? Here also the prediction is 0.5. So it indicates that model does not learn very much good thing, right? As we have only trained for five epochs, right? So you can take this code, you can build yourself with this data, and then we'll see that how good you are in deep learning basically, or how good you have understood the knowledge or the concept of Siamese network and basically multi-input neural networks. So here you can see one plot of predicted distance histogram. So it will come in it should come up like this, okay? But as the network does not learn anything with 5 epochs, it is not learning. So here you can see. So you can take this whole code and you can build yours, and you can point it out and comment down below that whether you have learned something new or not. If you have learned something, please give a like and a thumbs up and subscribe, share, and stay tuned with our channel. Bye.